DTIS. And so I will start with on the topic of seasonal snow. So why do we want to detect snow? I will start with a small example. So this is the catchment of the Durance in France, and you have the Verdon here at the bottom. So what happened in 2022? There was really a drought in the Gorge du Verdon, which is a very touristical place. So a lot of people didn't come, a lot of tourism didn't come, and it was a bad year for this region. But the problem is that water has to be shared between a lot of different people, so human to drink, people that want to do agriculture, hydroelectricity, and in this region, tourism as well. But in 2022, there was not much snow during the winter. And in that case, it has to be anticipated because, for example, one of the, so this project started as a collaboration with EDF. And what they do is that they produce hydroelectricity in the winter, thinking that snow will come in May when snow is melting, and that there will be water back in the river. But that year it didn't happen, so they managed to stop making hydroelectricity in March, but it should have been a bit anticipated. So that's the type of application that they want. They want to know how much there is snow at the moment to try to anticipate how much there will be water in the river in the summer. So this study is not focusing on the Verdon, but more on the Guil. That is also a river that goes into the Durance. And it's in the Queyras, if you know the mountain region in France. And it's a very interesting place because it has like mid-altitude. So you have snow that can fall in autumn, then first melt, then snow that comes back again, that falls again. So you have a lot of cycles. While if you go in the higher mountains, the snow that fall in autumn will generally stay for the whole snow season. So that's why we focus on the Guil. So how do you generally monitor snow? The most easy processing is to compute the normalized difference snow index. So in optical, you compare two different bands, generally green and SWIR. And here I show you two different products. The one on your left is the modest one. So you have 500 meter sampling, but you have data every day. So that is really nice. And on the other side, you have the latest snow Sentinel-2 product. So you have a final 10-meter resolution, but you have images only every 5 days. And as you can see, there can be a bit of cloud. There can be a bit of cloud. So on this part of the MODIS image, we don't have any information on the terrain below. So if we look at the cloud cover, basically what we can see is that we have a bit more snow in the valley, a bit more cloud, in the valley than in the top part of the Guil catchment. And so I was yesterday on an airplane above the Alps, and you could clearly see that there was the cloud and then the summit of the mountains that are above it. So that's a bit the phenomenon that you get. Generally, you have a bit more cloud in the valley. And the problem with that, so here also another image, the contrast is not very good, but basically there is generally a snow line. So you have no snow below an altitude and you have snow above this altitude. And the problem is that the current snow limit is approximately here, so between 1,250 meters and 1,050 meters. And here you don't have that much clouds, you can kind of see it, but the snow limit is forecasted to go up because of climate warming, and so it will be in the area where we have the much snow cover. So when we have issue with cloud, what do we generally do? We turn to SAR sensor. So I don't know if we can just remove the part. So how do we monitor snow with SAR images? So if we have both polarimetry and interferometry, we can try to detect directly the snow. But generally, what is done is that if we know that we have dry snow, it has been shown that the ratio between the two polarimetric channels of Sentinel-1 is proportional to the height of the snow. But that is if you know that you have snow, because a lot of other phenomena like vegetation can create a difference between these two polarization channels. And so you cannot detect snow using that information. What is easy to detect in SAR is the wet snow, because basically, so here I have a small GIF in Osfona, so in Svalbard. And if you look at the image in September, that will come back in a moment, you can see that it becomes very dark. So when there is water, it's snow. Basically, you don't have any backscattering, so you can easily detect wet snow. Yeah, so you could see a bit here, and now it's really dark. So you can detect wet snow by comparing a time when you don't have any snow and a time when there is wet snow. You can make that difference. So that was a method proposed by Nagler in the year 2000, and that has been used quite a lot. And you can see on this image that when, like it's in May, you can see the snow pattern, which is really good. So building on that knowledge, we decided to see, okay, so now I am really sorry, but I lost the, okay, yeah, so yeah, it's working. So we were trying to do it with AI, so how to detect snow, both wet and dry snow conjointly with AI. So we selected two studies area, the Gill catchment and the Gironde catchment that is just in the Écrin, but also a catchment, a river in the Durance catchment, in order to see what could be the spatial transfer. And we also had 2 years. So we trained only on 2018, 2019, and we kept also another year of data to test for temporal transfer. And we split the data set to have Sentinel, the date where we had Sentinel-2 image only in test. So we train on MODIS data that I will show after. And we can test on days where we also have Sentinel-2 to see what is the resolution that we gain. And I choose to do the training on SLC data, so I don't know if a lot of people know about SAR, but the goal was to do maybe interferometry, because we saw in previous article that interferometry could help. We didn't use it, but let's say. And so we have 3 Sentinel-1 orbits for this study. So basically, the first step is just to use the optical NDSE that we threshold to get label. We put that in a unit as a label for a unit. And as input, we tested multiple combinations, which are either our 2 channel, the 2 Sentinel-1 channel, also adding a reference image. And we also computed already the ratio that I showed you before, so the ratio of the polarimetric ratio, to see if well-managed channel could help the network. And so the first result was that you can detect both wet and dry snow with a unit, which was already a nice result. That having 4 channels, which are the 2 polarimetric channels and the 2 reference images, was the best choice. And if you look here at images, I mean, yeah, maybe on this is better, but basically when we compute the ratio, generally it's nice when you want to apply a simple threshold, because you remove all the topography effect of SAR images. But we think that the topography really helps our units to manage the detection of the snow. So inputting ratio didn't really help in that case. But the problem is that by using this method, we had 40% only of the pixels was a label because of the cloud cover. So we thought, can we use temporal interpolation basically to fill this gap and then have more labels for the training? So we compared 2 ways of doing the interpolation. The closest neighbor interpolation that is generally done on MODIS data. So basically you just do a linear interpolation between 2 dates if you have just 1 day of gap. And if you have more days of gap, you only add 1 one information just at t+1 or t-1. So that's one first interpolation. And the other interpolation is a Kalman smoothing. So in that case, we use the whole time series. We said that the change between the snow cover between two dates is linear, which is normally not, because generally when the snowfall, we have a huge gap. So we add a noise, and depending on the variance of this noise, the snow cover can move or not. And on the observation, we also added a noise on measurement. And it's basically the ratio between the variances of these two noises that help us to choose how much regularize. If the noise of the measurement is really high, then basically we will most likely not trust the observation and follow a smooth line. And in the contrary, if we have a big variance on the model noise, basically we say that our model can change a lot to follow the observation. Okay, so that are some examples with some of the Kalman smoothing. So as I said, when we have a large parameter eta, basically we are smoothing a lot and not really following the observation. And when we have a small eta, we are following more the observation. And what we also get is the variance of this time series if needed. So now we have the question, what is the best parameter eta for the Kalman smoothing? So basically, we look at the effect of eta, and what we can see is that when we increase this parameter, when we regularize more, we have less snow. So the proportion of snow, that's the top graph, is decreasing, and it's the same for the three orbits. I didn't put the color, but my three colors are my three orbits. And we also look at basically which eta was changing my label. And so below I showed in blue, it's when the Kalman smoother made change my label from no snow to snow. And in red, it's on the contrary. I have a label that has snow, and I go to no snow. So that's what happens more often. And I also looked, we also looked in the validation, what would be the best eta, and we settled on 0.3. So after this first parameterization of eta, we keep this value. And then we can compare on the unit what are the best results for the gill basin. And we can see that the Kalman smoother is a bit better than the others. And if we look at the image, basically what we see is that interpolating really helps to get smoother border. And when we look at temporal transfer, we can say that it's the same, but basically transferring temporally is very easy. You don't need too much to do, at least for that application. And then we went to spatial transfer, and we could see that interpolation was also improving a bit the results, but that on a new basin, it's a bit hard for the network to really follow the topography, and we kind of lose some details here and there on the map. So really, if we want to apply this method in the whole Alps, we need to train a bit more than in one basin, but that is okay. And then we could compare our model to the Let It Snow product. So I forgot again to put the dates, but we can see that basically on the Sentinel-2 products, we have a lot of details that we miss in our data, even if the SAR resolution is only 5 meters by 20 meters, which should be closer to the Sentinel-2 products. The fact that we have coarse resolution labels and a unit that is also kind of not very precise sometimes at the border, kind of smoothen a bit the information, but we are still quite happy with that solution. Okay, so on the topic of snow, basically what we have shown is that we can measure snow, we can detect snow from SAR images, and we can do that with having one map for wet and dry snow together. We don't have to create two products, and that if we interpolate the labels, it kind of helps. So it could be used in other applications like deforestation, where you have also a lot of cloud cover, even if you need to have the information at the right moment, because interpolation cannot really recreate some information. And so the future work is to test with this time using the Sentinel-2 labels. So we don't have any real label this time. We will interpolate the Sentinel-2 time series and try to do that again. And also to merge the optical and the SAR information using an implicit neural representation in order to get snow maps every day, merging all the information. So that was on snow, and now we will go further north. So still looking at what can be done in the cryosphere, but for sea ice. So I am not really sure if you know about sea ice, but basically sea ice is the ocean that's frozen and become ice. So it's very different from icebergs that come from land, basically. And on sea ice, you have the flow of ice, and then you have a lot of fracture between the flows that are called lids. So sea ice, banquise en français, is both the flows and the lids. And it's a seasonal pattern, so sea ice, basically the ocean freeze in September in the Arctic, and then the ice consolidates, and at the end of the season, you have sea ice melt, apart from some part of the Arctic, but this part is reducing with the years. So you have a thermodynamic process, the fact that the ice is building up to 3 meters in thickness, and it's also a dynamic process because the ice is drifting over the ocean because of the wind, because of the current. So this is a Sentinel-2 image over sea ice. And basically, it's very important to measure sea ice thickness if we want to understand what is currently happening with climate warming in the Arctic. The Arctic is one of the environments on Earth that is changing the most with the Mediterranean Sea. And when we have a reduction of sea ice, it can create a loop because sea ice has normally a high albedo, so it reduces the ocean warming, and also it insulates the atmosphere from the warm ocean. So basically, it decreases the energy budget. But if we have less sea ice, this loop will become more difficult to manage. And when people are modeling climate, it's very hard for them to use real observation of sea ice. Generally, they prefer to get the model, the sea ice thickness, the modeled sea ice thickness, because the sea ice thickness is hard to validate at the moment, and there is a lot of observation errors. So that we want to improve the sea ice thickness measurement so that it can be better assimilate in climate model. There is also another goal to monitoring sea ice. It's navigation at the poles. So in the Arctic, some people, not including myself, dreaming of crossing the Arctic with ships. For now, it's hard to cross, and you can only do it in summer. And for the there is also, of course, a military interest in the Arctic, and the same in the Antarctic. So in France, we have bases in Antarctic, so we need to know when to navigate to get food to this station. So I will also introduce you some concept, which is the marginal ice zone. So basically, you have normally the ice pack is where you have dense ice, more than 80% concentration. So the concentration of sea ice is the proportion between the flows and the surface that we are looking at. And you have the marginal ice zone that is at the boundary of the ice, and this boundary can change a lot. But since you have less ice, you have way more drift in the marginal ice zone. So it's really an area where you could maybe navigate, but you have to be very careful when you do it. So we want to measure a lot what happens in the marginal ice zone, and we can see that it's retreat. So this is Svalbard, that is at the north of Sweden, and we can see that we have less ice there in July, and then ice is coming back in September. So there is also, I am mostly focusing on the Arctic, but just as so that you know, basically, the sea ice is also very important in Antarctica, but a bit different, because in the Arctic, there is a land mass around it, so the ice cannot move too much, while in the Antarctic, the ice can move quite a lot. And also it's nearly disappearing in summer, but as a normal fashion. So for now, all the processing that I am doing is for the Arctic, but there will be a bit of domain shift when we want to go to Antarctica. So now we can look at sea ice. So here we are again in Svalbard, in the Storfjorden, and there is also a small animation of how sea ice evolve for like a week. And we can also see here the impact of the change in the swath of Sentinel. So we can see that the retrodiffusion on SAR image, the retrodiffusion of sea ice change a lot. And you can see also leads appearing and the ice moving a bit in that fjord. So just you have a bit of an idea of what is happening. So as I said, the information that we really want is CI thickness. That is what at the end we would like with the final resolution as possible, of course. And that is measured by radar altimeter or LiDAR altimeter. And I will describe a bit how we do that. But we need an altimeter that is a nadir-looking sensor. And when we don't have that, we can maybe do sea ice mapping only. And that would be the position of the flows and the leads, and maybe different type of classes for the ice. But what is generally mapped is just the concentration. So you have a lot of ice there or less ice there, and it already helps the ships to decide where they go. And we also need the sea ice drift, because then we can forecast where will be the ice. So these are the important parameters. And the sea ice mapping and the sea ice drift is computed from images. So radar sensor, Sentinel-1, RadarSat-2, optical imager, and the passive microwave. Okay. And in this presentation, I will focus on Sentinel-3, which is a platform that has multiple sensors, and that's why it's really interesting. So the two main sensors are OLCI, which is a multispectral imager. So it's making this image that is really just an extract of the image. The OLCI images are very, very large. And there is also SRAL, that is the radar altimeter. And an altimeter is just making a track like at the nadir. It's nadir altimetry. So we are only having some very limited information. We have also 30-meter along track resolution, but the spatial footprint is quite large, nearly 2 kilometers. So it's a bit, I mean, it's not the most precise of the sensor, but the only one that's unable to get precise elevation. So in the project that funded part of this work, the goal is to merge the images, SAR and optical, and altimetry. And to do that, we need a very precise sea ice drift, because we want, I mean, if the acquisition have not been done at the same time, so apart from Sentinel-3, generally, we don't have altimeter and image at the same time. We need to compensate the drift. And I will show you later what are the value of the drift. But the goal would then be to try to get information from the image, the texture of the image, to try to extrapolate a bit the thickness and try to get a bit larger thickness map. And I said they are SWOT-like, because SWOT is a new sensor launched by the CNES that is doing SWOT altimetry. And so the goal would be to bridge these two types of sensor. Okay, so now how do we measure the sea ice thickness? To do that, we use nadir altimetry. So basically, the altimeter is sending a pulse, measuring the time between emission and reception, and it can get the elevation of both the ice and the leads. Then we have to classify the waveform. So this signal, that is the energy through time, is called a waveform. We have to classify the waveform, said, okay, this is overflow, this is a lead, and we can use then these two information to compute the freeboard, that is the part of the sea ice that is above water. And then if we have an information about density, we can get the sea ice thickness. So the first information is to get the radar freeboard, and to do that, we have to classify leads and flow. So the classification is generally made on the fact that leads are very specular. So we get a lot of energy back, it's very peaky, while flows, it's more rough. So you get less energy at the top, and you have a slow decrease of the energy. So that is the information that is used in the current product that is called the pulse pickiness method. And basically they had a third class if the pulse pickiness, which is just the ratio between the maximum value and all the energy, so very simple, is it's below 0.1, then it's a flow. If it's above 0.3, it's a lead. And if it's the middle, we don't know, we don't take it into account to measure the thickness. And so now we need to validate the altimetric flow lead classification method in order to improve that product. So thanks to Olchi, we can get the image. So that is really something that did not exist before Sentinel-3. And so we can see that when the sensor is above a lead, we can get more information in the waveform, and then we have less information. So we want to use Olchi images to validate any flow lead classification, and maybe after to improve the classification of flow and leads. So to do that, Laura Weissgerber, which is the PhD working on that project, she has annotated a dataset because we don't have any annotation at this resolution. So she has labeled 400 pixels. So it's really pixels, the center of the image, that's the class, and that's the altimetric waveform. And we have created 5 classes. So the flow, the lead, we have also the brush ice, that is like small pieces of ice above which we can't really measure the elevation. Then we have pack ice that is larger, and thin ice, which is really when the ice starts to form. And she has annotated information in the Fram Strait, so also a bit of geography, but basically sea ice is created there and flows out of Arctic in the Fram Strait. So in the Fram Strait, you have a lot of fragmented ice and it's drifting a lot. And in the Beaufort Sea, on the contrary, you have way more like pack ice and large amounts of ice. And yes, sorry, I also forgot to say that basically we have 3 months because, but also I forgot to say again, is that because of the polar night, we don't have any optical information between basically November and February. So we have only information where we have sea ice and enough light to measure it with an optical sensor for these 3 months during the year. Yeah. So she created first confusion matrix between the 2 classes. But to do so, we have to create link between the class that we are seeing on the image and the class that the altimeter is seeing. So what we say is that flow is basically a flow. That's easy. The lead and the thin ice are normally lead as well. So even thin ice, you have a very peaky echoes, and also in terms of elevation, it's really close to the elevation of the ocean. So it should be put in the leads in the lead information. And then you have the brush ice that is basically everything else. So invalid lead and invalid flow. And using this classification, she had like only a 72% accuracy for the altimetric measurement based on the pulse pickiness. So basically, altimetry is not very good at classifying its own waveform, and that is a big issue. And so she then looked at all the well-classified waveform, and even in that case, even when the prediction, the hand label and the SRAL prediction were the same, you can have issues. So for example, here, you have basically leads that are close by, and you have side lobes of the acquisition. And so you get information from the leads. And so this, for example, this waveform should be rejected because it cannot be used as a measurement of the elevation because of this off-nadir leads. So very complicated topic. But then we have all the ambiguous waveforms. So again, we have an off-nadir lead here. And then here it's really weird because it's above a lead. It looks a bit like a lead, but not enough for the pulse pickiness method to work. So a bit weird. And then you have also other classification errors. So here Laura said that it's a flow, and the SRAL predictions say that it's a valid lead. So maybe there is a lead, a frozen lead here, but it's quite hard. Then you have other surprises, like here, basically it looks like a lid, but it's really large, so it can even be called a polynya. And you have strong wind that day, so the water is not as flat as for a lid, and the waveform looks a lot like the waveform of a flow. So you have a lot of weird phenomenon. And that was not, I mean, before the synchronization of Olsi and SRAL, we couldn't see all this information, and we couldn't know that that was happening, even if people were already thinking that it could, but it was hard to verify. So now we want to scale this analysis. And so we have used our data set. So again, only 400 pixels. And we have trained a very, very small CNN that work on very small patches to try to classify the center of these patches. And so that's the work of Etienne Senigou, that is currently an intern at ONERA. And if you look at an image, we can see that it's not too bad. So we have the leads that are sometimes well-defined. Here we have raw frozen leads, so it's okay. You have brush eyes at some point that shouldn't be there, but it's hard for a so small network to be able to do anything. So the image classification altimetry is 81%. So for now, it's kind of okay for Laura to do a bit of statistics between the classes of the altimeter and the classes of the image, and try to build a bit better sense of what is happening in the altimeter. So our goal now is try to estimate the influence of the leads of Nadir. And also a point that I didn't mention is that in summer, the snow over the sea ice is starting to melt and to create what is called melt ponds. And that reflects as a lead, but it's at the elevation of a flow. So we have also to try to add this class again. And then we would like to train a waveform classifier using the classes of the image. So to apply that for the whole year. And what would be the goal is then to extend this information at the scale of the image. So that was for Olchi. But what we also want to get, as I said, is the drift. So that's the work of Uda Assini, who is finishing a postdoc at the moment. And so the drift, so as I said, the sea ice is drifting, and it's drifting approximately by 6 kilometers a day. I mean, the mean of the drift in the Arctic is 6 kilometers a day. So it moves a lot. And in the marginal ice zone, it really can move a lot, like 20 kilometers per day. So you need to compensate that. And you have also a lot of small values in the pack ice. And part of it is fast ice. So again, a new vocabulary, but fast ice is ice that is close to the land and that is not moving because it's fastened to the land. Okay. So here I show you a Sentinel-2 image, which should be moving, but it's not fully moving. So here we have fast ice that is not moving. Here we have ice that is moving with a very discontinuous motion. And that's the current product from DTU, where they have a posting of 5 kilometers in both directions. So basically the motion is good, but it's very rough. So we want to do better than that. And to do that, we thought, okay, in optical flow, there is a lot of good networks. So let's use neural network of optical flow on this data. So we selected CRAFT. And then there is the problem of the training that I will show you a bit after. But basically, we took Sentinel-2 tiles that we divided in patches of 124 by 124. We focused only on the red band because it should be enough. We could have used RGB images, but we didn't. And so we have here the image 1, here the image 2, and then a GIF that is trying to show you what is the motion. So basically here we have a fracture that is closing. And we also have a drift in that direction. So I will take a bit of time to present you these examples because I will talk about them later on. We also have another set of image with its very simple translation, but there is not many, it's quite homogeneous. And also there is a change in the illumination between the two images. And a third case that I really like, that are individual flows. And we can see that one flow is going in that direction, another flow is going in that direction, and all the small flows around the big one are also moving their independent way. So there is a lot of different motion. And we don't have, so we need to do the retraining. I won't present that, but we don't have, sorry, I am going a bit too fast. So that's what CRAFT is doing when we look at the first case. So basically it's working a bit, but that is again the GIF of the image 1. That is where the motion has been compensated. And when normally it doesn't move, it means that the algorithm worked. We can see that it's not working very well. CRAFT, just taken off the shelf, doesn't work very well. On this image, it doesn't work at all because it's focused only on the fracture, so no compensation. And on the image of the small flows, again, not working very well. So we need to retrain it. And to do so, as Nicola introduced, we use the same philosophy as the flying chairs, which is we don't have real flows, so we will simulating the sea ice drift, but we don't want to have a very complicated model because flying chair has shown that optical flow methods don't need that, basically, and also there is no ocean model working at a 10-meter scale. So we cannot take any physical model to create a real drift. So what we do are very simple motion. So first a translation, a rotation, then a divergence. So we create a fracture and the two parts are going in opposite direction. I mean, one part is fixed and the other is translating. And the other image is shear, again, a fracture. One part of the image is fixed and the other is sliding. That are four type of motion. And the motion amplitude is between 0 and 500 pixels. So that is a bit less than the mean sea ice drift, but we will do tiling when we go to higher drifts. And yeah, so for each case, she simulated all these images. So we have 20 different cases. And for each of these cases, she creates 2,000 train images, a bit of validation and a bit of test. So I won't show you any tables, but basically we are improving a lot from the CRAFT, but I will show you images. So that's the first case. So apart from the fracture, we are really compensating the drift. The image is nearly not changing. The same for this translation. There is small fracture there, but basically with this new model, it's working very well. And again, for the different flows, we have still some flows that are not working well, but it's okay. But Uda was said, okay, I think I can do better. So she decided to basically only move one image, one flow in her image instead of moving the full image. And she did that using SAM. So using segment anything model, she selected flows in her image, applied again the same transformation. And so she has now two simulation types. So a bit less image in each case, but the same number of image in total. And that is the final result. So basically, we can see that we are sharper in the drift estimation. Here again, a bit sharper. And on the flow, this part was not compensated before. And you can see that now this flow is nearly not moving. So the fact to go at the flow level really improve the sea ice drift estimation, even for smaller feature. So we are quite happy with that algorithm. And now there is the issue of working on a full Sentinel-2 tile. So for now, she has just cropped the image in different patches, applied it independently. And what we can see is that in this part, we don't see the cropping, basically. Here we have a larger drift. Sorry, maybe we have a... Yeah. Here we have a larger drift. So there is a bit of a shift between two estimations. So we also have to work a bit on that. And now there is again the issues of cloud. So she showed that with thin cloud that are just kind of changing a bit the illumination algorithm is robust to that. Here we have a larger cloud, so the second image is nearly, still a thin cloud. We can still see the sea ice below, but still a larger one. And globally, we still have some errors, but we can still compensate quite a bit the drift. But when we have that much cloud, then the algorithm is not working. And I just want to show you this pattern because it's really like when CRAFT is failing, it's giving us this type of pattern. So the ongoing work is to do a pan-Arctic validation. And so first to compare with the existing DTU products, but also to compare it with buoys. So there are a lot of, not a lot, but there are some drifting buoys in the Arctic. And so you have their position along the time. So it took us quite a while to find Sentinel-2 pairs where we have sea ice, no clouds, a buoy, and try to get that to create a nice validation data set. And then the main issue that we still have is the issue of tiling. So we need to be able to detect when the model is wrong. So when it's clearly wrong, generally we have this, it's predicting value in all the directions. So this we can easily remove. But when it's not that wrong, it's a bit harder sometimes. Or we need to choose the best match between different tiles. And sometimes this, we have one piece of flow that goes into two different tiles afterwards. So part of the flow has to be estimated with two different tiles. And that is a bit hard. So the first idea is to work on the properties of the estimated drift. As I said, when it's clearly wrong, we can do that. And then it's based on the comparison between the warped image one compensated for the motion. And globally, it's also kind of working, except when we have illumination change. In that case, the algorithm says that it doesn't work even when it is working. So we have a bit of work to do on that part. And another stuff would be to detect first, before applying CRAFT, that the drift can be estimated. That would be also quite helpful. Okay, so as I said, all this work was done with Sentinel-2, but again, an optical sensor, and so we don't have information in the winter. So we are at the moment working with Michelangelo to try to map sea ice from SAR images. So here I show you a SAR image. We have the Sentinel-2 image projected on the Sentinel-1. It's also a bit in the same idea as what SWAN did. So from this Sentinel-2 image, we kind of get a label of the where are the leads, but not very precise. And it's very hard to get that from the Sentinel-1 image. So this image was denoised with Merlin, which was developed at Telecom Paris. And we can see basically here that we have a lead, here we have a lead, a larger one, and here we can a bit see this lead, but it's very, very faint. So we will see what we manage to get, what type of feature we manage to get using also part of a self-supervised approach. Because on some images, it's even harder to really see the correspondence between the optical image and the SAR SWAN. Okay, so that's the end of my presentation. I don't have a very nice conclusion apart that working on the cryosphere for me it's really nice. I really love when I have this type of environmental application. But there is a lot to do between to work with multiple sensors because as Nicola said, you have a lot of geometry to work out, a lot of physics also to understand what each sensor is seeing. And so, yeah, I hope to convince you that it's an interesting line of work.
Thank you very much, Flora. I really like that it shows like all of the efforts that are necessary to do useful things, actually, like actually useful things. Are there some questions in the room or online?
Yeah, about snow. It was a very interesting presentation. I was wondering if it is only a binary classification or if there are other kinds of applications. For example, you were talking about hydroelectric. Maybe is there a way to quantify how much water there will be or things like that?
So to be fair, that's the main goal. I didn't say it in the foundation, but the main output would be the snow water equivalent. The problem is that with the seabed of Sentinel-1, that is very, very hard to get. So people have done tests with a SAR on an airborne SAR, basically, and they show that in the Ka band, that is much shorter, they can get information about the snow water equivalent. But that would be the main information, and you have also a lot of information about the physics of the snow, like the different layers and so on that you would like to get, but it's becoming really hard to get that information from space at the moment, at least. But yeah, normally you want way more than just the position of the mapping of the snow. You really want the height, the snow water equivalent, and so on.
Thank you.
About the synthetic data set you created to fine-tune the optical flow model, I'm not sure I understood how you designed this data set and how you simulated the data.
So, I mean, we took the patches like this one, and then we apply, where was it? Was it after? Yeah, I think it was it. We applied either a translation on this image. So here you can see that there is new flow appearing because we have the full image. So we don't have to have black at the border. We also just rotate the flows. So this flow is going in that direction, basically. We apply a rotation. Then we create a fracture. One half of the image is not working. The other half is leaving the frame. Or like a shear, which it's also a fracture, but it's a sliding fracture. So these are all synthetic, and basically it was random. You choose the direction of randomly you choose the position of the fracture, its direction, and then the motion of the drift to have enough image in each categories, basically.
Okay, so you had to divide the images in patches?
Yeah, basically you cannot, I mean, a Sentinel-2 image is a very, very long script, and already ESA is styling it in some tiles.
Yeah.
And then we have to because, so that's the full, that's the full image. And at the end, you can see that it's divided in that type of tile. So here it's always a different types. That's the size on which we are making the optical flow matching. And yeah. Did you?
Yeah, I just I think you mentioned something about organization, and I was wondering how what's your view on those and how you apply them. I think you mentioned that during your
Yeah. So Swan that is in the room is currently working on that, so you can have a chat at the coffee break. But basically, for now, we have only used optical sensor as a label for the SAR image. But there is also, I mean, we are dependent on the way the SAR images are acquired. So basically, we have SAR images for 3 days, and then we have 3 days without acquisition. And so in order to get acquisition every day, we would like to also incorporate all the information. So we want to take, we want to build on the fact that with foundation models, you can have already an alignment between SAR and optical to try to do implicit neural representation in the latent space of this model, and basically saying at this position this time, that was the latent representation of my image, either SAR or optical, and then you have something that converts this token into snow map at the end to get the snow map at every moment that you want. But it's on a small area. So basically you have to train the model for every basin that you are doing. So that can be a bit of a limitation. But normally after that, you don't need to store any of the data, which is way more than, I mean, which is very, very large. And you can only store your small model. So I think it will be quite helpful.
Yeah, thank you.
Yes, I have a question regarding this somebody that has the generation. Would you contemplate doing like half self-supervised learning on real image and half supervised learning on generated image like this to improve the results, or do you think it's like?
I mean, we could. So in CRAFT we have an encoder, so we could maybe specialize the ResNet on this image with a self-supervised method or something else. For now, we thought that it was easier to retrain the full network with a synthetic drift, and it worked quite well. And also we have very large drift. But it's true that now if you want to apply that on SAR image, which is my current goal, I have to see how I can build nice features that then are well correlated here. And as I showed before, when we have two different orbits, the SAR backscattering change a lot. And so indeed, we will have to train that, and we are thinking of doing a self-supervised method to train that, and then keep these parts are already quite good. So we want to keep them from the optical or not change them too much, but we need to retrain that part. Yeah.
Yeah, and maybe even use some retrained encoder that was made to be, as you said, like similar between SAR and the optical. Like I think
we could do that. I mean, to be fair, I am not 100% sure yet, because the two SAR images that are acquired with two different orbits, they are in two different geometries. And so we need to put them in the same geometry for the drift that we estimate to be really the drift of the CIs and not the drift of the sensor geometry. And to do this resampling, that's why also we want maybe to use Merlin, because when we have denoised the SAR image, the resamplings make way more sense than when we have a lot of speckle. So maybe we need to do some pre-processing before, but I don't know yet how much. But yeah, normally that's something I am thinking about at the moment. Like also, yeah.
I have a question about the Kalman smoother that
Yeah.
you talked about. So you have the parameter,
Yeah.
that you said you fixed at
0.3.
yeah.
But it's-
Is this value, in your opinion, region dependent, date dependent, or something that you should maybe adjust if you go somewhere else? Because in the Kalman application, generally the adjustment is what gives the power estimation.
So it's at least application dependent, maybe also sensor a bit dependent, but I think basically what we want to say is, I think, so for snow, we have really sharp transition. And I think this sharp transition, I mean, maybe if at some place you had sharp transition all the time, you should use another value. But I think for the snow, mostly you have one sharp transition, maybe a second one. And so I think the Kalman smoother value can stay a bit the same, but I haven't tried. So I would say that for snow and for these two sensors, it's kind of okay. But if you want to apply it for another application and with other sensors, you may have to change it.
Maybe a small question. The project of Huda, in a way, you are creating data to train. I was wondering if we try to make the link with Nicolas' presentation this morning. Would it make sense to use generative models to create this data? Or because you are using quite a ad hoc method to do it, would it bring something to use generative models to create maybe more realistic data?
Yeah. I mean, I think it would, but it would take a lot of time.
And
so
would it be worth this time?
That I am not 100% sure, but maybe with SAR sensor we'll have to do it if we cannot. I mean, I was really surprised to see how optical flow networks worked, even with very crude flows, basically. So you can train them with quite easy flow, and at the end they worked on very complicated one. And that I didn't expect at first, but I think in that case, maybe it's not worth it to generate image to have, but in some cases, I think it might do. And so for some images, I would be quite happy to get that, but you have to simulate, because you have to simulate the SAR image, the drift, and then the change of the acquisition conditions. all the three together to have your, but yeah, of course, if that was available. But I don't know if I would personally do it now.
Okay. Any last question? If that's not the case, I propose we thank Flora.